Okay, good evening. Okay, first your assignment. Okay, this one is segment H. This is +1. So this one should be +1. Clear? Okay. So there's typo there. So +1. Okay, today we will go into new topics. Lecture week 9, trees. Now, all this while, what you have learned is actually called a list. So list is basically something that is changed in a linear or serial fashion. So that is a list. Now once you have graduated from a list, then you can go into more complex data structure. So the next one is tree. So if I were to put items in this fashion or in this order, then it becomes a tree. So a tree is basically a more advanced structure compared to a list. Okay? So you need to know a list before you learn tree. So tree is done. Okay? So now we move forward and we advance to a tree. Now you know what tree is. So this is a normal tree. You have leaves on top and then a bunch of branches and then you have root at the bottom. But this is the real tree. Our tree is a bit different. Okay? When you talk about a computing tree, the root is at the very top. And then the leaves is at the bottom. And so basically it's branching out upside down. Okay? Simply because your computing, even your monitor, the X is the same, but your Y is going down. Okay? So in computing, our Y axis is going down. That's positive. Going up is negative. So it's a bit different from the real world. Now there are many things that a list can do, okay? Many beneficial things. But there are things that is best represented using a tree. Especially if you have relationship where I have ancestors and descendant. So whenever you have something that hierarchical ordered, you have the parents, you have the child, that is best represented by a tree. For example, org chart, family tree, your file directory. Family tree, for example, there's a parent and then there's the children. So this is where tree excels. But everything depends on relationship. So whenever I create a tree, I need to specify the relationship. If you change the relationship, the tree will change. Okay? So relationship is very important in a tree. Everything is decided by relationship. So for example here, on top I have Carol, and then Brad, Jennifer, Brian, and then under Jennifer I have Jared and Jamie. Because I specify the children relationship, it means anything at the bottom are children. So I can define Jennifer and Brian as children of Carol, or Jared and Jamie as children of Jennifer, based on the relationship. Now, if I change the relationship from children to parenthood, now my diagram will change as well. So you can see now on top is Jared, and then I have John and Jennifer at the bottom, okay? Because now whatever below Jared is parent. So this is why the relationship is very important, okay? So you build the tree based on relationship. So different relationship result in different diagram. Org chart, organization chart. You have president on top, vice president, dean, chair, and then bunch of sleeve down here, okay? Your folder, file directories. Now when we see our file directories, this is what we see. It's like a list, but actually it's not a list. Your tree is decoded into a tree structure. Your folder is into a tree structure. So actually this is a tree. So when you click, then you will see more. So all these are put inside a tree structure, okay? So all your OS, even Mac for example, there's a type of tree that is used to organize all the folder and file that you have created. So now we go into the terminology. Now a tree is a set of nodes connected by edges. So these are called nodes. All these are called nodes, 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 nodes. And the line that you see here are called edges, okay? So that edge indicates the relationship, okay, between two nodes. And they are arranged by level. So this is one level, one level, one level, one level, or also known as height. Now the top level is called a root, and at the bottom, not necessarily at the bottom, anywhere in your level, if that node has no children, we call that a leaf. For example, these are all leaves. These are also leaf, a leaf, leaves. Okay, so you can see here the root level, and then the children and sibling. For example, these two are sibling, okay? But G and H are not sibling. Clear? If they share the same parents, then they are sibling. Now, some start from 0, meaning level 0, 1, 2, 3. Some start with 1, 2, 3, 4. But it doesn't really matter, okay? Because the total height is still 4. So normally our concern is more on the total height. Okay, by now you know what children are, and then parents, sibling, leaf node, no children. Now the only node without any parent is the root. So you can see every single edge has parent, because every single node has one edge. Every single node has one edge, one edge, one edge, one edge, except root. Root has no edge, okay, because it has no parent. So node is reached by a path. The height of the tree is number of level. Okay, and then the node degree. Now, node degree is basically the number of children. Let's say, for example, this is your family. So Joe has 3 children. So the node degree for Joe is 3. John has one child, Chris. So the node degree for John is 1. And Chris has no children. So the node degree is 0. Clear? Very simple. Okay? Total number of children. And then you have 3 degree. Now 3 degree is the maximum of nodes degree. Now you don't count everything. Basically the maximum means who has more children. So for example, in your family, your uncle that is most productive, okay, have most children, that is the 3 degree. Clear? Okay. So for example, in this case, Joe has most children, 1, 2, 3. So the 3 degree is 3. Clear? Now there are many different types of tree. You have 3 with 3 children, 3 with 4 children, 3 with thousands of children. But there is one particular tree that interests us the most, which is binary tree. Now the reason is your computing is 1 and 0. Binary numbers, 1 and 0. So binary tree can solve a lot of computing problem. Okay? Because our computer is represented by 1 and 0, true or false, if-else statement. So in a binary tree, your node has at most 2 children. Binary, okay? Now these are some of the definition of the binary tree that you need to know, okay? Otherwise, when you get an exam paper that says this is a complete tree, then you'll be confused. Or the paper say, assume that the tree is a full tree. Then answer the question. Or assume that the tree is a complete tree. Then answer the question. So you have no idea what is a full tree, what is a complete tree, what is a tree is not full and not complete, then you may answer wrongly. Clear? Now full tree is quite easy. If I have 3 levels, then all 3 levels are filled up. Okay? So it's full. If I have 4 levels, then all 4 levels are full. That is full tree. Clear? Now complete tree, now although the name is a complete tree, but actually it is not complete. Okay? Complete tree is not really complete. The name is complete tree. Now complete tree is actually a full tree, but it is not very complete. It is missing the ending, okay? Missing at the end. And that is a complete tree. So it doesn't have this, it doesn't have this, it doesn't have this. So it misses at the end. Remember, in a binary tree, the way that you read is from top, then you go to the left, go to the right, go to the left, right, go to the left and right. That's how you read, okay, in a binary tree. So in this case, the missing is at the end. So it becomes a complete tree. Now, if I were to take this out, now this is not a complete tree anymore. It becomes tree that is not complete and not full. Clear? If I take this out, then it becomes complete tree. Clear? If I take this out, then it becomes not complete tree. Clear? So make sure you understand the definition. If I want this to become a full tree, then all I need to do is just add this. And now it becomes full tree. If I want this tree to become a complete tree, then I need to add this, this one, and this one. Now it becomes a complete tree. If I add another one here, then it becomes full tree. Clear? Any question? 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 Now, those of you taking the alternate test, you need to sit here. Okay, so this is the introduction to binary tree. Now, difference between a tree and binary tree. Now, this is the same as the difference between your linked list and a stack, or linked list and a queue. So your linked list cannot be empty, okay? But the stack can be empty. Tree cannot be empty. You need to have at least one items, one node, which is the root. But binary tree can be totally empty. Okay, the tree degree cannot be more than 2 because maximum 2 children. And in binary tree, the tree is ordered, okay, because it's a number. For example, this is number 1, number 2, number 3, number 4, number 5, number 6, 7, 8, 9, and so on. So there's a fixed number associated with every position in a binary tree. Okay? So this is one example of the use of binary tree. You can use arithmetic expression tree because most arithmetic has that binary relationship. Okay, binary tree properties. Now you don't need to remember the formula. Okay, you don't need to remember the formula. All these are common sense. So just make sure you have some sort of common sense, okay? In binary tree with n elements, you have exactly n minus 1 edges. What does it mean? If I have 3 elements, how many lines? 3 minus 1, 2. Why? Because every single node has parent, so it has line, except the root. So that's why you minus 1. That minus 1 is for the root. Okay? So if I have 1, 2, 3, 4, 5, 6, 7, 7 elements, meaning I only have 6 lines. 1, 2, 3, 4, 5, 6. Okay? Minus 1. Clear? Common sense, common sense. Okay, you don't need to remember the formula. Now, a binary tree of height h. Height is this. So, for example, this is height 2. This is height 3. Okay? It has at least h element. Now, at least means minimum. If the height is 2, minimum is 2. If the height is 3, minimum is 3 element, 3 nodes inside. Why? Because if the height is 2, the least I can put is 2 nodes. 1, 2. If the height is 3, I can put something like this, 1, 2, 3. So it's 3 elements. Clear? Common sense. At most means if you try to fill up everything, what is the most number of element? 2h minus 1. If the height is 2, then maximum is 3. If the height is 3, then the maximum is 1, 2, 3, 4, 5, 6, 7. Clear? 2 to the 3 minus 1, 7. Or if you don't have the formula, you don't remember the formula, you don't have the calculator, then you can do manually. Height of 4, 1, 2, 3, 4. Then count one by one. Clear? If you don't want to count one by one, then you can basically just do something like this. 1, 2, 4, 8. These are the number of elements inside each level. So the total number of elements is 8 plus 4 plus 2 plus 1, which is 15. Clear? Or if you don't want to add everything, this 15 is basically 16 minus 1. Then you don't really need to calculate. Clear? Okay? So up to you. Most of the 3 is basically just common sense. Okay? You can try to remember the formula, or you can just try to get the common sense out of it. So you need to remember for the formula. You can see there's some more formula, but it's just common sense. Now, just now, you are given the height, okay? Now you are given the number of elements. So let's say you are given 4 elements, okay? So you are given 4 elements, 1, 2, 3, 4. The maximum height I can create is 1, 2, 3, 4. Same with the number of elements. But if I want to get minimum, then you pack everything. So if I have 4, I have 1, 2, 3, 4. So I will get 3. Okay? Height of 3. Clear? Or you can, if you want to use the formula, 4 plus 5, log to 5. Log to 5 is 2 point something. So 2 point something shilling, you get 3. Clear? So you can use the formula, or you can use common sense. Okay? So in a binary tree, you have fixed number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 15, and it continues on and on, on and on. Okay, it's a fixed number. Parents. So if you are given number 8, for example, what is the parent? Divide by 2, 4. Clear? 13. If you divide by 2, you get 6.5. There is no 0.5, so it is 6. Just divide by 2, okay? Now, the only node that has no parent is the root. Okay, root has no parent. Every single node has parent except the root. Now, the opposite of it is children. So given node number 4, where's the children? Times 2. But because we have the left and right children, the first one is times 2, the second one is times 2 plus 1. Okay, 8 and 9. Clear? But you need to be very, very careful. If parent, every single node has parent except the root. But not for children. For example, if the question asks, what is children number 15? Then you say 30 and 31. You get 0. There's no children because the maximum is 15. Okay? So for children, you have to be very, very careful. You need to know the entire total of the notes. Then only you can tell whether there's a children or not. Clear? So how do we represent the tree? Now, similar to your list, if I want to represent the list, I can use array, or I can use pointer. So one is static, the other one is dynamic. Same thing. So if I want to represent a tree, I can use array or I can use a linked list. Now the reason that you can use array is because in binary tree, every single position already has number. So we can use this number to create the position in our array. So this is our array, and then we use this position to put the element based on that position. Okay? So, for example, E is 5. So this is position 5. 0, 1, 2, 3, 4, 5. So inside position 5, I put E, which is this one. Okay? But because it's an array, there will be limit to the level. So you need to decide upfront how many levels for this particular binary tree. You cannot exceed that maximum. But it's a problem with binary tree. When you have incomplete binary tree, you can see there's a lot of missing spaces. Okay? And it gets worse if it is skewed. You can imagine if it is skewed to the right, all these position that you have reserved for an array is empty, nothing. So even though you only have 4 elements, you still need to have 15 slots, okay? So this is the reason why binary tree is not really efficient if we try to represent this using array. That's the reason why most binary tree will be represented using linked lists, your favorite pointers. And how to do that? It's quite easy. Remember, you have learned double linked lists. So in your double linked list, okay, you have data, and then you have next, which is a pointer, and then you have previous, which is another pointer. So this point to the next, this point to the previous. It's the same thing, except instead of next and previous, we name this as left and right. So left point to the left, right point to the right. That's it. Clear? This is a C definition of structure. Okay, yours will be much, much simpler. And these are some of the 3 operations. Okay. Any question? Any question? 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 Okay. let me get back to your assessment, your assignment. Now, in your assignment, there is this okay, students expected to participate in the group works during tutorial. Half individual mark will be deducted from each non-participation. Now, I will not deduct any marks, okay? So no marks will be deducted. So if you did not come for whatever reason, no marks will be deducted. Clear? Instead, it will be counted as extra credit. So if you come, then you get that half participation marks. Clear? Okay? So the same thing goes for your subgroup. Okay, so no marks to be deducted. Okay, but if that particular day is the official group discussion day, then if you are there, then you will get half marks. Clear? So don't worry if you are sick and so on. Okay, no marks will be deducted. Okay, and then next week you're supposed to get back your paper. Okay, so when you receive your paper, we will go through the question, each question, and then you're supposed to check. If you are not present at that point, so basically the marks will be counted as official. Clear? So you will get the paper and then you will check, and if there's any discrepancy or anything that you want to protest, you need to protest during that lecture. Clear? If you cannot come, you can, for example, ask your friend to check the marks, check the paper for you, not a problem. Okay? The paper will be given and you can take it and keep it. Okay? Clear? Any question? Any question? Any question? Any question? Okay, for your tutorial this week, okay, we will do analysis of algorithm using timer. Now, what happened is from the code, we analyze the code, and from that we get our complexity expression. Okay, so from this we can get the dominant term, and from the dominant term you can get your big O. But what if the code is very, very complex? It's just not possible to come up with all this. Then as the last resort, we use machine to run. Clear? So checking your algorithm using machine is actually not your first option. It's actually your last option. Okay? So we use the machine and then we check and we try to get the growth rate. It could be like this, could be like this, it could be like this, could be like this, could be like this, like this. So from this, we can determine whether it's exponential or whether it's logarithmic or constant or whether it's linear. But in order to make sure it's accurate, we cannot use online GDB. Because online GDB, the time is not really accurate. okay, because it is a shared server. So your running time is based on the running time at that particular moment. If there are many people running, then the time will be affected, okay? So this is the only time when you're supposed to run using your machine, meaning the compiler need to be inside the machine, okay? So because it's only one program, so it is not mandatory, okay? So if you want, you can run, but because you need to have a local machine, local compiler. Or you can just observe, or you can run using online and see if the result makes sense, okay? Up to you, okay? But I'm using local machine, local compiler, but only for that program. The rest, you can still use online GDB, online compiler. Clear? Okay, for this week tutorial only, okay? Any questions so far? Any question? Question? Question about your assignment? Question? 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 Okay, your attendance. Once you in attendance, you can leave.
Betul bang. Yang bang surat apa? No sampah, bukan di sempah. Then what? You guys say what? Okay. Betul bang. No, we have to just say sempah. Maybe it's a military.
Yeah, I need more elaboration. Okay, yeah. I think there's a.
So, for the search part of the presentation, right? Do we only explain the code, or do we need to show, oh, this is how this search functions, blah, 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 with the diagrams?
It says searching complexity algorithm code development, analysis, and conclusion. So there is nothing about how actually that search works.
Oh, okay. So I just show the code, show how complex it is, and then.
But of course you still need to run.
Oh, it's still need to run.
but not like the sort where you need to explain how it works.
And for the visual representation, right? Oh wait, no, I got it clear. I need to do all this in 6 to 7 minutes.
The entire thing is 6-7 minutes. How you want to manage the timing is up to you.
I'm okay.
You can edit the video, right? Like make cuts.
You were in the same group. You were in the same group.
Make it faster.
I know. It's okay.
Alright, that's it. Yes, sir.
Okay, thank you, sir.
Just take it.
Oh yeah. Bye.